Okay, guys, I thought I would hop on here because I'm already getting some questions about this simulation part, the exploring the hydrogen model, that back page of this virtual lab assignment. It can be a little bit confusing at first because you're going to see a lot of information at your eyeballs, and it's going to make you feel like, what did Miss Sabatka make me do? So I thought I'd just kind of open it up with you guys and kind of show you or explain what you're looking at to where your head can kind of be in the right frame of mind to answer the questions. So we're going to go to the Phet simulation link. We're going to click on the energy levels tab. Okay, and this is what you see when you open it up. There are three visuals that you can look at here. This first picture right here in the middle is the Bohr model of the atom. What you can see, this is the hydrogen atom, and that little blue thing spiraling around that red nucleus is hydrogen's one electron that is found in energy level 1 at its ground state. Okay, now over here is the electron energy level diagram. Look, it is showing hydrogen's electron here at the energy level n equals 1. So whenever you see n equals, it's telling you what energy level that is. I think we mentioned also in class that the distances between the energy levels are not all the same. As you can see, there's a giant jump in between energy level 1 and energy level 2. And then it gets kind of smaller and smaller and smaller. The distance in between the energy levels represents how much energy is either required to jump up and then how much energy will be emitted from the falling down, okay? Now, keep in mind, we talked about on our electromagnetic spectrum, depending on the energy of any type of light, we have variations in wavelength and frequency and stuff like that. So we know over here on my high energy side of my spectrum where the gamma is, that's going to be very different than my low energy spectra over by the radio waves, right? So we're going to hopefully start to see here when we hit the buttons and get things going that, higher energy colors of light and maybe stuff that is not even colored outside of the visible spectrum will be represented by longer, bigger, higher energy jumps. And stuff that's over here, that lower energy side of the spectrum, will probably be represented by some shorter transitions in here. Okay, so I can also pop down here. This is the third visual thing I'm going to see. So this is the visible spectrum, you guys. Only a short little chunk of it. It has this visible range for our colors of the rainbow. And it has the two regions that are just slightly outside of the visible spectrum. If you'll notice, this is kind of a flipped version of our electromagnetic spectrum that we did in class, meaning the lower energy side of this spectrum is over here, okay? And then the higher energy side is over here in the UV direction. So it's just a flippity flop, not a big deal. So what you're gonna see is when we hit the buttons to start firing photons of energy at this atom and seeing if we can get that electron to jump, is this down here is the spectrometer is gonna kind of start creating a tally of whatever photons were able to be emitted from this electron in response to getting excited and then falling down, okay? What I like to do is I like to look at both the Bohr model and the energy level kind of side by side. And it does take a second for you to kind of figure out what it is that you are seeing, but I did want to give y'all this head start. So after I get everything ready to go, let's see, what does it say? We are going to make sure the Bohr model is selected. It is selected. We feel good about that. And then we're going to come down here and make sure the white light version is selected. We have done that. And once we have done that, we are going to click on the red button on the light source to turn it on. So what we are watching now is all of these different colors are photons of light going at the atom, okay? They are different colors because each photon has a different wavelength. Okay, now if you'll notice, some of these photons are colors like red or orange or yellow or green or blue or indigo. Yes, if they are colored like that, that means those are photons of light that are going to be represented inside of this visible spectrum. I also see photons of light that are gray. That just means outside of my visible spectrum. It could be either lower energy than my visible spectrum, but also it could be higher energy. Okay, now I mostly like to jump to the energy level diagram here. These ziggity-zag lines are actually showing the energies of the different wavelengths of light trying to make these jumps. Whenever you see a gray one, that just means that light energy is outside of the visible spectrum, whether it is too low energy or too high energy. Okay, every now and then you will see a colored wavelength in this energy level diagram, and that just means that the energies specified or required for that transition happens to fall within the visible spectrum here. So one thing I'm noticing immediately is, well, that big gap between energy level 1 and 2 is already making me nervous. And yeah, I'm probably not going to see any colors of the rainbows in here. I probably expect that it will be gray getting from energy level 1 to 2 because that is a big gap in energy. I have to have a super energetic photon of light to get up to the second energy level. So I'm expecting when I see that transition for that to be on the higher energy side outside of my visible spectrum. Does that make sense? Also up here in the teeny tiny transitions, that also may be gray, but gray for different reasons. Not gray because it is too energetic to be in my visible spectrum, but gray because it's not, or it's so low energy, less energetic than it would be inside of my visible spectrum. So down here on the bottom are on our spectrometer representation of the electromagnetic spectrum, it's kind of keeping a running tally here of all of the potentials, photons of light that were given off from falling down of that electron inside of this atom. Okay, so here we see the energy input of the photons of light going at the electron, and that electron sometimes will absorb that energy where he goes from his ground state of energy level 1 to his excited state. And then anytime he falls down, he is going to fall back down to his ground state, but in the process of that, he's emitting light. So jump up to excited is absorb, fall down to ground is emit. So this spectrometer is mapping the photons that this electron is emitting. Yes? So a lot of, oh, and see there's kind of a blue color that went from 4 to 2. So that's pretty exciting. So there are some guided questions in there. And next, I think it has you change the wavelengths to only allow certain wavelengths of light. So I think the first transition that it has you do, moving into analysis question number 3, is then you're going to set your wavelength to 103 nanometers. So it says for you to click on the transition buttons. And what I want you guys to notice over here is there's different buttons that represent different wavelengths that you can select. Also over here, it shows what energy level transition that is the exact amount of wavelength or the exact wavelength required for that jump. So like this one is the amount that's required for a transition from energy level 1 to 6. Well, that's a real big jump. And that's my smallest number on this chart. Well, a small number for wavelength means a short wavelength. Oh yeah, a short wavelength means a high energy. So of course it makes sense that that really, really big jump from 1 to 6 is going to be represented by the highest energy and therefore also the lowest wavelength light, okay? Now, one thing I also notice here is I can see that nice visual. All of these guys, these high energy stuff, I can't see, but boom, once I hit a wavelength of 410, I am in the violet. I can see visible, 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 visible. I hit red on the low energy form of the visible spectrum, and once I get high or longer wavelength than that, I can't see it anymore. Too low energy for me. So what's kind of fun to do is to look at the numbers here and be like, oh, okay, yeah, a 5 to 6 transition. Ooh, yeah, it's not a lot of space up in there. So of course it probably will not take a ton of energy, which means it'll be lower energy outside of my rainbow visible light spectrum. Anyway, that was a tangent. Hopefully that in some way helped you guys, but it does have you first select the 103 wavelength, and they tell you that that is the exact energy required to get from 1 to 3. So obviously I'm making that jump, and that's really exciting. So you can see, we already talked about that. Oh, it's gray, probably because it's pretty high energy for, but every now and then, I think I saw something. Oh, it stopped at energy level 2 sometimes. And I noticed that that was red. So I'm going to let you guys chew through this. The rest of the assignment has you, I think, select a couple of other different wavelengths. But I thought I would hop on here just to kind of describe what it means when you see these gray particles, what it means when you see the colors, and relate that in terms of energy and wavelength and all that fun stuff. But there's some other fun things that you can play around with this, and I think it's a really fun simulation to mess around with, but you do not have to do anything that is beyond the requirements of this lab handout. So I hope that was helpful. You guys message me if y'all are confused or need extra questions or help, but I love how the spectrometer at the bottom really shows that distinct bands that tells us that, yo, these energies are quantized. I cannot just get all possible wavelengths to create a wonderful full electromagnetic spectrum of allowed possible photons. It's only certain ones due to these energy level transitions. Okay, I'm going. Thank you guys so much. We will see y'all later.